All right, we can start. 1 minute late. So we'll talk about a lot today, and you'll want to capture as much as you can. Because we're going to do the little short lecture on the structural analysis paper. So you're going to want a calculator, you're going to want to follow along and be like super tuned in. And it's going to be super confusing because I'm going to cover 2 classes in 40 minutes. Yeah, that's exciting. It's a little bit like the fundamental engineering exam class. If you take the class, fundamentals of engineering exam class covers a complete course every. So like you come in one night and then we'll do statics all in 1 minute, and they'll bring in the statics instructor to be like covering calculus in 1 minute. Nuts. All right, what's going on next week first? Good. So who got the email? It's a better show of hands. You should raise your hand whether you got it or not. All right. So you know that you go on to Blackboard and please sign up for the lab. You are in. If you go on the field trip, because I have to give them a list of names, and I only want to send them in with folks that are actually going to go. So if you're going to go, you got to get your name in Blackboard. You got to get it in there by tomorrow, by Friday. Because I'm going to submit the name Friday. If you can move from Tuesday lab to Thursday, if you can move from Tuesday lab to Thursday lab, do that for me. But I only need 4 of you, so. Like, check the numbers first. So if you're someone who can move, submit a link, right? Let the numbers kind of develop, and we'll just see how it goes. If the numbers look balanced, later today or something, then just say you're up, right? But if you're really to jump to the Thursday lab to balance out the numbers, it should be 20/20, but I don't think everyone's tuned in, so mine had to be like 19 to 19, 18 to 19, or something like that. That's fine.
But what should we do if we are like working to improve?
Just yourself. Just go in and submit your stuff. Okay. For your lab, for the day that you will go on the Zoom. Anyone need a ride?
You need a ride?
Anyone need a ride? I don't need a ride. No one needs a ride. Everyone's got their carpool figured out, but we're all just gonna be super American and drive individuals. Right? We're going to drive our own beast of the road. And it's better for everything. Okay, good. Any questions on anything before I get zooming? No, we're good. Okay. I've heard that before. So what I'm going to do first before I go through my spiel is I did load up some examples of some structural calculations just so you can see them. They're under today. I'll start with this is our homework format that we put out. If you're going to be in a course, I shouldn't say all of us, but I do it in all my classes, and then other instructors who have been here a while also will produce something similar to this. And it's for calculation-based courses. If you're going to be creating calculations in a class, it should follow a kind of a specific format. So you could think about this format when you do your structural piece on your project. This is a little confusing, I think, so let me just kind of walk through the basics of it. Essentially, name, date, course, that kind of stuff for a class that you're submitting calcs in kind of on a regular basis, right? That information should be on there. So for your structural paper, obviously, you're going to have the same kind of thing. You're going to have information about your lab partners, the date, that kind of stuff. This is actually working problems out of a book, so they have named the problem statement. It's a good idea, and then the next ones I'll show you that are actually calculation packages. Every calculation section has a title to it. So whether that's a tensile stress analysis or a bending stress analysis or just some kind of a static analysis, it'll have a little title to that area of the calculations. So you should have the same thing. There's normally a graphic of some kind. If you're going to do it by hand, just make it nice and neat and use a straight edge and be all engineerish with it. If you're going to use a computer, then that'll be a little more computer generated. This is very academic now. You're not going to see this on the other packages produced by engineers, but this is good for classes that have multiple different theories that you're going to apply. For example, today you're going to get tensile stress and bending stress. Those are two different theories, right? So it's good to note, like, the concepts that you're using. This is the tensile stress analysis. That analysis is different than a bending stress. Okay, so they would be like categorized differently, not all combined. So this is just stating the theory that was used in the calculations down below. Assumptions are super important. So you'll have a bunch of assumptions you'll have to make about your project when you go to do this little project on calculations or structural analysis, right? So you might assume that the material, if you're working with the material and you don't know what it is, you might make an assumption. For example, today, I might make an assumption about what this is made out of because I don't know what it's made of. What is it? The general material is wood. What kind of wood? Beats me, and is it a combination? Maybe land, maybe. Oh no, it's solid. But I don't know what kind of wood it is. Are there different woods? Yeah. Are there different strengths to woods? Big time. So is maple different than Doug fir, different than hem fir, different than oak? Absolutely. So most of our wood in this area that we use for structure is fir. Yeah, Douglas fir. Okay, but then we grade wood. Is it Douglas fir number 1 or is it Douglas fir number 2? Right? Or is it high strength Doug fir? All depends on whether we can find a knot in it or however they graded it. Right? So there's all different kinds of assumptions that can be made on projects. So if you make assumptions, just note them. You want everyone to know if you've made an assumption. Okay? And then the solution of the calculations should be, if they're hand done, as nice and neat and organized as possible, and should go left to right, top to bottom. Left to right, just like we write, it can work across if there's multiple calculations that feed to each other, and then it should work down. So don't do work kind of in the middle of the page and then have arrows pointing up to the top of the page and then the arrow going back down to the bottom of the page. That's just not good. All right. So that's the first example. Let's go for a little more of a calc package. So I think this is a hand set. Oh, this is just a homework set. We don't need this one. Let's go to a hand set. So this one is my garage from 1996. When I built my garage, right? And this is Dowler Engineering. So the way that I worked with him was I produced the calcs, sent it to him, and then he reproduced my same calcs and stamped them. But you can see that's the thing right there. That's the professional engineer's stamp to the document. Come back, come on, there we go. Right? So if you become a PE, you get the stamp. Like they mail it to you. It's all fancy. It's brass. And it literally stamps. This is a copy, but it stamps the paper, like embosses it. It's super cool. And then they sign it. So this is acceptable to the county, and the county's not going to touch it because Gerald is taking full responsibility for this, not the county. If the county changes anything, then the county takes responsibility for it, and they don't want that. So they'll let the professional engineer be responsible for it. These are pretty sure they're lateral and shear calcs. So these are, and he did it by hand in 96. Actually, this guy was retired, so I'm not sure he'd ever seen a computer before. He was old in 96.
But he was just doing this out of his, basement kind of thing for folks like me who needed it done. So these are stud fasteners called out, required stud fasteners, required studs, and then required holds for this structure of a garage. Now my garage, half of it's on land, right? Sitting solid on the ground, but then my land drops pretty severely, about 10 feet. So half of the garage is up on 8-foot concrete columns. So that anything like that requires structural engineering. If my whole garage was just on the dirt, then I can just follow prescriptive code and build it. And I don't need a structural engineer, right? But anytime it gets anything tricky, anything not traditional, then engineering is going to be required. So let's look at how he organized his. So he has some kind of fun because these are hand drawings. He has some hand drawings of some details that are important in the package. He's got some hand drawings of, oh, it's 2 stories too. Here you can see the grade change, right? And then he just goes into all kinds of shear calculations. V stands for shear, not too important for you yet, but you'll get there when you get into shear stress. But shear is the building's resistance to any kind of side shifting. So that's both seismic and wind, right? You don't want the wind to blow hard on a box and then just like it'll fold it over if it's not structurally sound. So this is how he set his calcs up. I just wanted you to see hand versions. Good. I mean, they flow top to bottom, they have a title, and they just go across. They all do refer to one of his drawings, that's great strategy, right? So it can all be correlated back. All right, and then the other example. I don't know why I'm having to go back there every time I click on something, but this is the 2 jobs ago that I did. And this is Ned Engineering, Ryan Nedke, right here. Same kind of thing. I have the project. I need a structural engineer. I took some walls out of a house, and you can't just do that, folks. So don't just go busting walls out of your house. Some of those walls hold up your roof, just so you know. So if they're load-bearing walls, you can't just pop them out of there and hope everything stays up. So when you do take them out, then you put beams in typically. So that's what I did for this family. Again, there's a stamp, right? And then he does everything on a PC. So his calcs are not by hand. And that's what they look like. This is a 2nd floor 2x10 Doug fir larch. Number 2 calls out the material, right? This is a floor joist, 1 piece, and then those are the calcs for the floor joist. So you're going to take, whether you're 2-year or 4-year, you will take static and strength of materials here on this campus. Jonathan has statics now, right? Yeah. So this is all statics and strength of materials. This you will understand once you get through the course. So that's what's to come. As you go through, he does another one here. This is a 3.5 by 15-inch beam. So that's one of the beams I put in place of a wall, right? So all that load that's being carried on that 2nd floor carries by this beam and allows us to take the wall out. So he's just going through and verifying. This is the load. The blue is the load. And then the span, 12-foot 1. I don't know where the 1 inch came from, Ryan, but that's all right. And then on and on and on. Again, this gets submitted to the county. They're not going to touch it. Here's a 5.5-inch beam by 9. They were big beams. So that's another way to do calcs, right? With a computer. I'm expecting you just to do them by hand. All right, what are you going to do? So first conversation is about loads. So your structure is gonna have some loads on it. You have to assume those loads. In other words, you don't have a lot of knowledge about loads yet, but what are the loads or could be the loads on your structure from your project once it gets out there and deployed? What could the loads be on? Wind, rain, snow. That's probably it. Wind, rain, and snow. I'm not going to seismic for sure. Right? How much load do you think rain produces? 5 pounds per square feet. 5 pounds? What do you got? A flat road? Like it'll hold up a smooth? I Googled it. If you have any kind of slope rain, it doesn't what? Yeah, it comes up. So any kind of a slope roof in the state of Oregon, there is no rain. I mean, that load is could be like, I don't know, quarter pound. Now, if you got a flat roof, then it's a whole different game. I suggest you don't do a flat roof, but you can do that. But you'd have to go to the 100-year flood or the 100-year storm, which is like 3 inches an hour of rain, and say that happens for 3 hours, which is what we do this time. At least for technology, for water, is a inch an hour, 3 hours, 3 inches of rain kind of thing, right? You don't have to do that. You have any kind of slope of rain. Wind, we're gonna ignore because it's very complicated. So we're just gonna do snow, right? In our region, snow load is about 30 pounds per square foot. On the mountains, closer to 50, and then so that's the load that you can think about. When something's loaded, what carries the load? The structure does. And if the structure just sits there, it carries the same load as the load put on it. In other words, when it snows, this building holds that load as long as everything's static and nothing moves. Right? So the same kind of thing is your structure has to carry that load. So that's how you determine how much load is on certain pieces. All I'm looking for is you do a little calculation on one little piece of your structure. Right? If you want to kind of raise your level, then you'll do 2 calculations. And I'll show you 2 that can be done pretty easily. All right, so equilibrium is this state of everything is equal to 0. So the building right here is in equilibrium, although that weighs a lot up there, right? There's thousands of pounds of stuff up there. Beams and roofing material and wires and plumbing and lights, and there's a tons of stuff up there, right? But nothing's moving in the structure. So the sum of all the forces, both the down forces and the up forces, is equal to 0. Meaning that if you have 1,000 pounds coming down, this ground should be able to hold 1,000 pounds going up. That's summing the forces to 0. Okay? And that works in the X direction too. If the earth shakes and creates, 1,000 pounds of load this way, the structure, if it doesn't fall down, then it supported that. It carried it, right? It fought back at that. So there's 3 things. There's down force and the equal up force. That's summing forces in the Y. Y direction is vertical. Good? X direction is this way. Same thing. Any forces this way, we equal it with forces this way. That's summing your forces in the X and Y. And the last thing is the moments, summing forces or summing rotational effects. So you might know what a torque is. Like if you take a wrench and you try and twist a bolt, right? That's a torque. Not to engineers, it's a moment. Same thing, we just call it a moment in statics and strengths. And then down the road later, we call it a torque. So we just switch it up back and forth, right? So the rotational effect is important. So we have some rotational effects in some things and not in others. All right, that's equilibrium. In statics, that's the state. Static means not moving. That means that those three things are true if it's not moving. All right. So what you can do with this information is you can think about any object that has a load on it, and we can isolate that object, understand what the forces are. For example, we have this pulley thing, right? That's gonna lift up your structure and set it down. It's gonna have to lift it by a certain spot, a point on your structure, right? So that's a great spot to do some kind of analysis. Because we know the load in the rope and we know the load going to your structure, right? Depends on how much load you put on the rope. If it was 50 pounds, it's a 4-to-1, that's 200 pounds that can go to your structure. That make sense? All right, so if there's an attachment point, you know the load on that attachment point. You can figure it out. You do gotta know the weight of your structure. Like not your prototype, the real structure. So if you're building this thing out of plywood or whatever you're building out of, you'll have to somehow quantify or come up with or approximate the weight of it. Okay, and then if your attachment point, your attachment point can be anything. I'm just gonna make something up though, so we can do a little calculation with it, right? So I'm gonna say your attachment point is some kind of a eye bolt. Maybe yours is not, but for my example, I'm gonna say that it's this kind of a attachment point. Can you see this? Yes. All right. So an eye bolt looks something like this, right? Comes down. And then usually has some threads, and then we're gonna put a nut on it. And then some kind of structure comes off of this thing. Right? And maybe there's multiple pieces, and then we put a washer on here just so we don't fail in bending or bearing stress. But we're not going to talk about bearing stress. So this is like a side view of my eye bolt. That makes sense? And this is attached to my structure. Like this is the single point that we're going to pick it up. How much is my structure going to weigh? Somebody give me a number. How much? 400 pounds. So here's my structure, and that weight, right? 400 pounds. Again, you can guess at this. Now, if my structure did weigh 400 pounds, how much is on the rope on the poor person in the flatbed? 100 pounds. I think that might be too much for that poor person in the flatbed. So be careful with that. If this was 100 pounds, then the person would have 25, right? 4-to-1. All right, but we're going to do the 400. That's all right. Yep.
I researched how much like person would weigh, and me and Mike agreed that like the general consensus for the maximum amount that should be for a person,
Yeah.
should be like around 200.
No plan.
Yeah, just because like some people
I mean, maybe the average person 200 pounds, but on a full of rope, much more than 50 pounds is a struggle. 50 pounds is a struggle. That's a lot of load to pull like that, right? If I weigh 160 pounds and I got 160 pounds to pull the rope, then I'm floating in air, right? I'm sliding off the flatbed. So just be careful with that. All right, so 400 pounds down, we know the sum of the forces are equal to 0. Even though we do want to lift the thing, we still treat it as equilibrium, right? So that means how much here? 400. So that means how much here, right across that little cross section? That 400 travels through this eye bolt, right? So it's 400 on the eye bolt. It's 400 on the threads of the nut. All of those are different calculations we could do, but you don't have to, right? But the full analysis of this thing would be not only the eye bolt itself, it would be the threads of the nut, it would be the washer on the material, because we don't want the washer just to suck through the material. Like if the material was styrofoam, that's probably not gonna work. The washer's just gonna suck right through it. That's called a bearing failure. So there's a lot of analysis that can go on here. We're just doing one little piece, just showing one example. We're gonna do this thing, and I'm gonna say this is a 1/4 inch in diameter steel. What kind of steel? Are there different kinds of steel? Oh yeah, it's endless, folks. Like, to do the full analysis, we'd have to know exactly what this thing is. And if you just bought the damn eye bolt at Ace Hardware, it's not gonna say what it is. It's gonna say steel eye bolt. Like, oh, great. There's only 500 different kinds of steels. What is this thing, right? It might have a load rating, which is helpful. And the load rating hopefully was more than 400 if you bought it for this application, right? All right, 1/4 inch diameter. Everyone understands the diameter of a circle, right? All right. So a basic tensile stress, I'm going to call it S sub T. It'll come to you differently. Some books will use the Greek letters and sigma for stress, but I'm going to use S for stress and T for tensile. So if you're pulling something apart, just trying to pull it apart, that's a tensile stress. If you're trying to bend something, that's a bending stress, right? And if I'm trying to rotate it, I can even rotate this thing, that's a torsional stress. You get all these in strength of materials. That's all later. All right. The equation for tensile stress is P over A. Super simple. Like most of our life is load over area. Oh, I just gave you a hint on what P equals. P equals load. Yeah. What's our load? 400 pounds. What do you think area is? Oh, what do you think A stands for? That's a fail. You would have got that, right? Area of what? The idle thing, yeah. So it's not just the idle thing, it's an area of failure, or the area that you're interested in. Whatever you're trying to do, the tensile stress is the area, right? Huh? The weakest link. The weakest link, but we often do, like if I was doing a tensile stress, it would be I'm gonna call it tensile stress. If I was doing a tensile stress of the threads where the nut is connected to the threads, it's literally the amount of area that would shear off if the nut came off the shaft. And there's ways to calculate, right? But let me tell you, there's a lot of area. When we spin a nut on threads, there's a lot of area there. It's very deceiving. They'll carry a lot of load. All right, what's our area? It's a circle and it's a 1/4 inch. Anyone know the area of a circle equation? Pi r squared. So it's not a 1/4 inch, is it? It's an 1/8 inch. Anyone know the decimal equivalent to an 1/8? 0.125 inches squared. Pi r squared, correct? Yeah, calculate that for me. Okay. Pi r squared. That's my pi. You don't like my pi? That's a pretty good pi. Oh. Isn't that the equation? Pi r squared. What's pi? That could be a midterm exam question. All right, what's my number here? For stress? 8. Just give me the numbers. I can't hear. Again, louder. 8149. I'm serious, I cannot hear. I think it's the fan. I'm gonna blame it on something. And is there more?
Yeah, there's like the actual number is 81487
4857333. Good enough. 8148.5733. Yeah? What are the units? What are the units of this?
PSI.
Pounds over
Right.
inches squared. Pounds over inches squared. Pounds over inch squared is PSI. Isn't that what we put in our tires? PSI? Yes, it is. It is pounds per inch squared. Same thing we put in our tires. So your tire should be like 33, 35 PSI if it's a car tire, somewhere in there, right? It's the same thing, it's a pressure. This material is feeling a pressure. How much? 8,000 PSI of pressure. What do you think this little item is gonna do? How do we know what it's gonna do? It has material properties. If it's steel, it has material properties. So we can look those up. Right? That's what we do, is we do a calculation. And we don't say, oh, that's a big number, or oh, that's a small number. We take that number and we compare it to something. Anytime we do a calc like this, we're only doing it so we can compare it to something. If this was regular A36 steel, this regular steel that you can just buy anywhere, the yield strength for A36 is 36,000 PSI. And that's the yield strength. That means at 36,000 PSI, that steel yields. It's just like permanently deformed. It doesn't fail. It just permanently deforms. That's why this country fell in love with steel. It is freaking strong, man. It's awesome. This little, I don't carry that. It's 4-inch. I'm getting made for 4 inches. Carry no problem. All your farmers that are putting in that 1/2-inch bolt just because you don't know, it's like way too big. Farmers are the worst. All right, there it is. A simple basic tensile stress calculation. This would get compared to whatever the steel is. Let's say it's A36. The key there is 36. The yield, so the stress yield, that should be a Y. 36,000 PSI.
What's the lower thing? Like, is it feet?
The one I just made?
Yeah.
That's a stress yield. So Y. And that's just a basic limit that we use, but typically we don't want to design right to yield. Right? If we do that, then there's a very good chance the material will yield. We don't want things to permanently deform. That's a bad thing, right? So normally we take the 36,000 and we apply a factor of 60. Right? So what's our factor of 60? If we're at about 8,000 and the limit is 36, our factor of safety is approximately 8 times 3 is 24, 8 times 4 is 32. We're just a little over a factor of safety of 4 with our little factor. Instead of money for this project, right? That's an example of what I'm looking for. There's one simple little calculation. Okay. I think we're still 2 weeks away from your structural calculation paper. So I'll do bending on Monday. Because bending stress would be another really not simple, but not too difficult calculation to do on some structural piece of your project. Cool. Bending stress, MC over I. I can start into it a little bit. We have a little time.
Question, what is the 836, that's the grade of the.
That's the grade of the steel, yeah. Yep. So if you look, if you're like, nah, we don't want to use steel, we want to use titanium, man. We want to use modern materials, right? Well, that's a whole, it has a whole different set of material properties. So
The thing that we love as engineers about steel is it does a beautiful deformation. It'll deform way before it fails. Right, and it actually goes through what's called the strain hardening region. So after it meets its yield and it deforms, it gets harder. It is the most amazing material. Obviously, we use it in absolutely everything all the time. Right? But that's why we love it. Is it's like very elastic. I mean, you get these steel, you're like, yeah, this is not elastic, it's solid as rock. But for a living material, it's very elastic. Has great stretch to it. And that's a good thing. You want things to deform and stretch before they go blow up, right? Titanium is the opposite. Super strong, light, no defense. So the first titanium bicycles that came out, they were awesome. They were light, super competitive, and when they broke, they just blew up. And just shards of titanium came out and went into people's heads. It was not great. Those bikes literally just exploded. Where a good chrome moly, chrome moly we used forever. When you jump that too hard or hit a rock or something, it bends up. You're like, oh, my bike's done. It's all bent up. I'm fine. No one got hurt, right?
Maybe I got hurt, but
That's
not,
where,
not from the bike failure, but titanium.
that's where it's very similar to like why, metal cars switched over to, like more plastic cars. Because like plastic.
Right.
Like crumpled and like.
So those first titanium bikes, they were like 1-to-1, no factor of safety. So then they started producing titanium bikes that had a bit more factor of safety in certain regions. So you'll find that bike design has changed a lot, but near the high stress areas, the geometries get big, and away from the high stress areas, the geometries get smaller. So they've come a long ways. All right, bending stress. So tensile is just yarding something straight apart. That's tensile, right? If you flip the load and you point it in, what is it? Compressive, yeah. Same analysis to some degree. If it's a long object, then we have to think about buckling and 100 other things. So what's super fun is you're gonna go through classes that does each one of these things, right? And in the end, they're gonna like hope you can put it all together. So, it's the next level stuff. Tensile. You should be able to find a spot in your project to do that kind of analysis. All right, this one will be a little more of a struggle to find a spot, but you can simplify your structure into something we can do it on. So if you want help and you want to do a bending stress, I'm totally available to help you figure it out. So, because it's a little more complicated, but that's the concept. You have a beam. The beam is supported at both ends. It gets loaded, and this is just the simplest load you can put on a beam. The beams get a lot more complicated than this, like next level complicated. But then that bottom part is the deflection curve, right? So when you load something and you have two supports out here and one load coming down, all of those forces equate to 0. In other words, if that was 500 down in the middle. Oh, what'd you say? 400 down, 400 down here, right? How much is here? 200. And how much is here? 200. Thank goodness they put it in the middle, because if it was not in the middle, then we got to do some fancy math to figure it out, right? All right. So yeah, 200 down, 400, 200. All right. So what we want to know is how much bending stress is there. And again, that's a property. I can look up the bending stress for steel. I can look up the bending stress for Doug-Fir. Doug-Fir is 900 PSI. Again, PSI, that's how we deal with stress, right? Steel, 47 PSI. So, you know, those are much different materials. But the equation's a little more, not gnarly, it's just more complicated than load over area. M stands for moment, C stands for the distance from the neutral axis to the outermost fiber. gets complicated. And then I, area moment of inertia. Okay, so we'll do that one, but again, it's just going to give us a stress, and then we needed to compare it to the material that we used. Cool. All right, we'll finish it up on Tuesday. See you in lab. I did record it, so. I think I'm 4 for 9.